Hello guys, hello everybody, hello world, hello Philippines. So at this moment in time, I will be able to, to have a live session and live discussion of problem solving about uh, thermodynamics. Okay, and that is a science how thermal energy is converted from one form to another in a matter. Okay, thermo means thermal energy, and then dynamics meaning motion. Thermal energy is the process of heat driven by the change in temperature, right? Inom sa akong coffee ha before to mag-start problem solving. Oh my gosh. Oh no. This is coffee without sugar. Oh my gosh. This really lowers high blood pressure if you don't mix sugar. Ganon. Okay, start that up. Here is the problem. Okay, so a reversible heat engine operates with two environments. In the first, it draws 12,000 kilowatt from a source at 400 degrees Celsius, and in the second, it draws 25,000 kilowatts from a source at 100 degrees Celsius. In both operations, the engine rejects heat to a thermal sink at 20 degrees Celsius. Determine the operation in which the engine delivers more power. So this is a comparison, okay, between heat engine number 1 and heat engine number 2. So the first thing to do, class, is we need to identify what law of thermodynamics really is the problem. So its example here is a heat engine. Heat engine is an example of, so you will choose whether it's zero law of thermodynamics, first law of thermodynamics, second law of thermodynamics, and third law of thermodynamics. So what's this all about? Heat energy, and then heat engine, or shall we say a car heat engine. Okay, so this is second law of thermodynamics, talking about car heat engine. Okay, so meaning to say the change in internal energy is zero. So meaning to say the heat energy is the result of the work done on the system, right? Because work is positive siya. Okay, so Q is equals to W, right? Automatically. Oh my gosh. Or the heat is completely used up for the work done on the system. So heat energy is equals to the work done on the system. On because it's positive work. Okay, let's start now. Okay, so we need to draw and illustrate two heat engines. Okay, the problem, class, states withdraws 25,000 kilowatts here, but it looks like this is a power. Okay, but don't be afraid with the unit kilowatts, okay, because that's still also an energy. Okay, like this. So 1 kilowatt hour is equals to 1 kilojoules per second, right? So this is heat engine 1, okay. Heat engine 1 and heat engine 2. Okay, so this is gonna be like this. It's gonna be like this. So this is gonna be like this. Okay, class, and this is gonna be like this. So this is our illustration. Heat engine 1 and heat engine 2. Okay, this is all engines. Okay, now in the first environment, the first heat engine draws 12,000 kilowatts from a source at 400 degrees Celsius. So we have temperature 1 equal to 400 degrees Celsius. This one, 400 degrees Celsius, and it draws 12,000 kilowatts from a source. So it draws 12,000 kilowatts, meaning to say this is a positive heat. Okay, $12,000 kilowatt. Okay, like this. Okay, Q is the, you know, the heat is being absorbed, right? Like this. Okay, and then we have reversible heat engine operates in the first it draws 2,000 and the source 4 degrees Celsius. Okay, and in the second it withdraws 25,000 kilowatt hours. So like this. Okay, 25,000 kilowatt, and then the temperature is 100 degrees Celsius. 100 degrees Celsius. So, okay, in the second, it draws 25,000 kilowatts from a source at 100 degrees Celsius. In both operations, meaning in heat engine 1 and engine 2, the engine rejects heat to a thermal sink at 20 degrees Celsius. So rejects heat. So meaning to say this is negative. Okay, 20 degrees Celsius. Okay, from both heat engine 1, so T2, 20 degrees Celsius. Okay, class, since this is a heat engine, so we need the formula of efficiency, right? So if you can remember in physics, it's just the same with the mechanical advantage is equals to work output divided by work input times 100. Okay, something like that. So we just state that Q is equal to W. Okay, so here we need input. So this Q here is an input for the heat engine 1. So this Q1 is heat input, right? Like that. And this one also is the heat input at heat engine number 2. So we need to solve the efficiency. So efficiency is equals to work output, right? So we need work output, or it's just equal to work over Q1, like this, right? Work output is equals to work input. Okay, and this Q1 apostrophe is just equals to work because the change in the terminal energy is equal to 0. Q is equal to W. Okay, and then we have, so the work output now will be the heat, okay, from the source, and then minus the heat from this part here, from the sink. There's heat also here from 400 degrees Celsius, and there's also heat here. Okay, so this is work is equals to Q1 minus Q2. Okay, work is equals to Q1 minus Q2, meaning, okay, the heat here and the heat here. Okay, so substitute this value here. Okay, so it will become now Q1 minus Q2 over Q1 1, like this. Okay, So Q1 minus Q2 or Q1 apostrophe, because W is Q1 minus Q2. Okay, like this. Okay, so now we need to get the formula of heat. Heat is equals to Q is equals to MC P dt, mass times specific heat capacity times the change in temperature, delta change in temperature, final temperature minus initial temperature, something like that. Okay. Okay, so now in the second heat engine also we have W is equals to Q1 Q2. Okay, efficiency also is equals to work divided by Q2 apostrophe. Okay, or shall we say Q2 apostrophe like this, like that. So we need to have an equal value of Q2 apostrophe, so this just equal this to Q1 apostrophe. Okay, or Q1 apostrophe. Okay, for this system alone. Okay, Q1 apostrophe also. Okay, instead of putting it as Q2 apostrophe, we may write that as Q1 apostrophe also in this system individually. Okay, so equals to Q1 like this. So efficiency is equals to Q1 like this, efficiency. So work is equals to Q1 apostrophe also. This is just a representation that's in this system only. Okay, and then we have also Q1 minus Q2 Q1 apostrophe. Actually they have the same formula because they have the same, this is the same heat engine in the second law of thermodynamics. Only the representation of the symbol, okay, I changed to make it parallel with the other side. Okay, because for the reason that these heat engines are just identically similar. Okay, so no need to change the, you know, the symbol in representing the solution, something like that. Okay, okay, now Q is equals to MCP dt. Okay, Q is equals to MCP dt, mass the specific heat of change in temperature. Now the specific heat capacity is 1 calorie per gram degree Celsius. We have the temperatures here, but our problem here is we don't have the mass. What we will do with these heat engines? We have the formula Q is equals to MCP dt, right? And then we don't have the mass, and we don't have morning. We don't have the specific heat capacity also. Okay, so what we're trying to do now for this, okay, we need to get another formula of heat, which is from the enthalpy. So delta H is equals to heat, because enthalpy is the heat energy transferred. It's just equals to heat. Okay, something like that. So we have the formula of temperature times the delta change in entropy. So you will choose between this entropy formula with relationship with the enthalpy, right? And then we have also the Q here. So this enthalpy, okay, may be applicable, but take note this is relating to entropy of the system. So relating entropy is in the third law of thermodynamics, right? Third law. So it will not be applied, this one. So all we have to do here is to treat the mass constant and the specific heat constant, because in the heat engine it is not specified there there's a water component inside the heat engine. Okay, so we may like this. Constant. So if it is constant, the mass of the specific heat, so it will become Q is equals to delta change in temperature only. Since we have Q here, Q1, Q2 over Q1 apostrophe, so it will be just equal to 400 degrees Celsius minus 20 degrees Celsius over 20 degrees Celsius. This one. So 400 degrees Celsius minus 20 degrees Celsius over 20 degrees Celsius. Because this Q1 apostrophe, the temperature in the Q1, which is that this is 20 degrees Celsius. And in the Q1 also at the top is 20 degrees Celsius. Okay, 400 degrees Celsius minus 20 degrees Celsius, something like that. Okay? Because we treat mass constant and the specific heat. Okay? Something like that. Now we will solve. So W is equals to 400 plus 273 minus 20 plus 273, 20 plus 273 times Q1, which is 12,000 kilowatts. This one. So we need to convert the degrees Celsius, 400 degrees Celsius to Kelvin. So 400 plus 273 minus 20 plus 273 over 20 plus 273. Okay, times the heat draws, which is equals to 12,000 kilowatts. So we have now the work here. The work done by the system of heat engine 1. Okay, let's calculate this one. 400 plus 273, 673. So 20 plus 273, 293, 293 times 12,000. So 673 minus 293 divided by 293 times 12,000. 673 minus 293 divided by 293 times 12,000. So 15,563 kilowatts. For the first heat engine, we have 15,563 kilowatt. And for the second heat engine, so we have 100 plus 273 minus 20 plus 273, okay, over 20 plus 273. So this is equal to T1 minus T2 over T1. Okay, so our work will be equal to multiplied by 25,000. This one. Okay, the same thing with heat engine 1, the same story. Okay, work over Q1 apostrophe is the efficiency. So work is equal to Q1 minus Q2 over Q1 apostrophe, or this is equal to the T1 minus T2 over T1, because these are the temperatures obtained by these heats. Okay, then we have, okay, 100 plus 273, because we need to convert the Celsius to Kelvin, minus 20 plus 273 from here, 20 degrees Celsius and 100 degrees Celsius. So then times the Q1 apostrophe here, which is equal to the 25,000 kilowatts, something like that. Okay, so our answer will be, so 20 plus 273, 100 plus 2 minus 293 times 25,000, 100 plus 273 minus 293 divided by 293 times 0.2730 times 25,000, 6,085. 673 minus 293 divided by 293 times 12,000. Okay, 6,825. So in the second, we have 6,000. What's this? 6,825. 6,825 kilowatts. And the other one is 15,000 plus. So it's the heat engine one that will operate in a more power, that delivers more power. So it answers the question here. Determine, okay, is that? Determine the operations that involve more power between the two. So it's the heat engine number one that draws more power, equal to 15,563 kilowatts, and the heat engine number two is only 6,125 kilowatts. So it's heat engine one delivers more power compared to the heat engine number one. Something like that, okay? So the first thing to do really to solve the problem related to related to thermodynamics, we need to identify what laws are that, or what is law is applicable for that, because each law has its own formula, okay? Then you can apply. And sometimes also, not really sometimes, most of the times, you will also troubleshoot what really quantities you made it constant, because throughout the process it doesn't mention there. Specifically for water, it's usually used, but if there's no water involved there, so we cannot apply the specific heat of water like that, especially there's no mass involved. For example, in here, right, in here there's no mass of water, and it's not mentioned the mass of the gasoline, the mass of the fuel. So in the theoretical aspects of the heat engine, it assumes to be that the mass and specific heat constant is just equal to constant, then, or irrelevant or negligible. We can see that heat is just equal to the change in the temperature. Q is equals to delta T. That's why we have Q is equals to Q1 minus Q2, and then Q is equals to T1 minus T2 na lang siya. Okay? Since we have the formula of efficiency, work output is equals to work input times 100, and we know also that in this second law of thermodynamics that the change in internal energy, okay, is zero. So we can say that the heat is just equal automatically to work. So that's why I have the denominator of work at the top, okay, over Q at the denominator, because Q and W is just equal, okay? And then there's a value of Q that draws in heat engine, which is 12,000 kilowatt in the first heat engine, okay, 25,000 kilowatt in the second heat engine. So we can substitute that there, and there's no problem anymore. We can solve for what is required, which is the W, or the work. Okay, do not be confused with the power in electrical energy. Remember that one, power is equal to work over time, because this is not related to electrical energy. So the kind of problem is not talking about the Ohm's law. It's not talking about the electrons flow in the circuit or in the path. Okay, this is not the work this is not the rate at which the electrical energy is transferred to a circuit. Though the word is power, okay, because that's kilowatts, but just try to think that kilowatt can also be a unit of an energy, okay? And electrical energy is also an example of electrical energy, okay? Electrical energy, mechanical energy, like that, thermal energy, heat energy, okay? There's a lot of energy: hydraulic energy, pneumatic energy, okay, sound energy, acoustic energy, potential energy, kinetic energy, light energy, something like that, okay? Geothermal energy, radiation energy, something like this. So there's a lot of energies around us, so we will not limit to the general term energy. But for us, for human being, we limit ourselves to energy as a heat energy, because we can do our work every day, we have the strength, we have the energy, so we obtain heat energy through the food we eat every day. Especially we gain different calories from different substances that we eat every day. So especially mainly the glucoses that gives us energy, carbohydrates, energy giving food. So that's energy that referring there is the chemical energy transformed to heat energy, because when we do our work we release this heat during metabolism. Okay, when we do exercise, when we do our work, especially lifting of materials, so it's in there that the calories is being burned, so heat energy is released. Okay, so and food is literally a chemical energy, and then it transforms to heat energy during metabolism cycle. Okay, and it gives us energy, mainly the carbohydrates. Okay, so that's specific for the heat energy and the chemical energy. But here it talks about the the heat energy and the heat engine. Of course, there's a mention very clear, heat engine. Okay, so we can say in this problem pala that the best example of the second law of thermodynamics is the car heat engine, or any vehicle heat engine, or heavy equipment heat engine is an example of the second law of thermodynamics. Okay, like that. So obligate siya sa equation na ani. Okay? Okay. Actually, it obeys the equation sa delta change in energy is equals to Q minus W. It just happened that the change in internal energy is 0. That's why heat is equals to work. Okay? Like this. Okay, so delta change in energy is equals to 0. So delta U is equals to Q minus W. So Q is equals to U. This one. This one. Just memorize this one. In second law of thermodynamics, the change in internal energy is 0. So if internal energy is equals to Q minus W, then therefore Q is equals to W. Okay? Meaning to say, all heat energy is completely used for the work done in the system. Okay? So the heat engine is doing the work, okay, to draw 12,000 kilowatts and 25,000 kilowatts respectively of the two heat engines. Okay, thank you so much for watching this live video regarding second law of thermodynamics, reversible heat engines. Bye bye. Thank you so much.